Discovery on the seafloor along the Cascadia Subduction Zone.
That's the same zone that could someday give Western Washington.
Beneath Vancouver Island, something ominous is brewing, and it's more than just a tremor. Geologists are raising red flags as seismic activity surges along the infamous Cascadia Subduction Zone, one of the world's most dangerous fault lines. This spike has scientists asking, could this be the start of the Big One, a catastrophic earthquake that's long overdue? As tension builds deep underground, one urgent question rises to the surface. Are we truly prepared for what could come next? A sleeping giant stirs beneath Vancouver. In late April, a series of shallow earthquakes began rumbling beneath the coastal waters west of Vancouver Island. While isolated quakes are not uncommon in this region, what happened next caught the attention of seismologists around the world. Within a matter of days, seismic sensors recorded over a dozen micro-earthquakes, all clustered near a particularly locked segment of the Cascadia Subduction Zone, a fault line known for its eerie silence and catastrophic potential. To understand the weight of this development, you need to know what makes this fault different. The Cascadia Subduction Zone is not your typical fault. It's not the San Andreas, where quakes happen frequently and noisily. Cascadia is stealthy. It builds pressure quietly, storing centuries of tectonic strain before unleashing it in one massive, continent-shifting earthquake. The last time that happened, January 26, 1700, a magnitude 9 event that created a tsunami so powerful it crossed the Pacific and struck Japan, leaving behind a trail of destruction and confusion. Now, more than 300 years later, the signs are surfacing again. INSAR, Interferometric Synthetic Aperture Radar. Satellites operated by the European Space Agency began detecting strange uplift patterns along the Vancouver coastline. Ground stations confirmed this, showing areas shifting vertically by up to 3 centimeters, roughly 1 inch, in just a few weeks. That kind of movement, geologists say, is anything but normal. What's more, GPS arrays along the island have begun to drift laterally, indicating not just vertical deformation, but significant horizontal stress buildup. These shifts suggest that the fault may no longer be slipping gently, but grinding to a halt, locking up the way it did before 1700. In seismology, a locked zone is a loaded gun. The longer it stays locked, the bigger the eventual quake. What makes this even more unsettling is the phenomenon known as episodic tremor and slip, or ETS. These are low-frequency seismic events that occur deep within the fault, often acting like a silent prelude to major activity. Over the last month, ETS events have surged particularly near the transition zone of Cascadia, just off Vancouver Island. More than 2,000 of these tremors have been recorded, migrating slowly toward the most locked and dangerous segments of the fault. If that sounds bad, wait until you see the tsunami models. Because when Cascadia finally goes, it's not just Vancouver at risk, it's the entire Pacific Rim. The tsunami threat, while a megaquake along the Cascadia Subduction Zone would bring devastating shaking to British Columbia and the US Pacific Northwest, the real killer might arrive after the tremors stop. Tsunami researchers have long warned that Cascadia is capable of producing tsunami waves exceeding 20 meters, roughly the height of a 6-story building. The terrifying part, these waves could hit shorelines within 15 to 30 minutes of the quake, leaving almost no time to escape. To understand why, we have to look at the structure of the subduction zone itself. Cascadia is what's called a megathrust fault, where the oceanic Juan de Fuca plate is diving beneath the continental North American plate. When this interface locks up and then snaps, it can displace hundreds of kilometers of ocean floor in a matter of seconds. That sudden shift vertically lifts or drops the seafloor, forcing an enormous volume of water upward. The result is a tsunami, one that can travel across the ocean at speeds of up to 800 kilometers per hour, about the speed of a commercial jet. Computer simulations from Natural Resources Canada show that in a worst-case scenario, low-lying coastal towns like Tofino, Ucluelet, and Port Alberni could be inundated in less than half an hour. Some models even suggest waves striking within 20 minutes, too fast for many communities to respond unless they have clear evacuation routes and functioning alert systems. The tragic truth is that many towns still lack both, and what's worse, there's a dangerous false sense of security in many parts of the region. Unlike Japan, where tsunami culture is deeply ingrained in the national psyche thanks to centuries of disaster law, much of British Columbia and the Pacific Northwest remain underprepared. Sirens, signs, and drills exist, but not consistently, and not always in places where they're most needed. Emergency managers have warned for years that complacency, not infrastructure, might be the region's greatest vulnerability. Let's not forget the 2011 Tohoku earthquake in Japan, a magnitude 9 event that produced a tsunami powerful enough to overwhelm the Fukushima nuclear plant, despite its high sea walls. The waves destroyed entire towns, killed over 20,000 people, and left hundreds of thousands homeless. Yet Japan had tsunami training, evacuation drills, and vertical shelters. British Columbia? Far fewer of those resources are currently in place. British Columbia is now starting to roll out vertical evacuation towers in high-risk zones, designed to give people in flat, coastal areas somewhere to go when they cannot reach high ground in time. But many of these projects are still in early stages. For now, the best-case scenario still depends on people running to hills or scrambling up narrow roads with a wall of water chasing them. And tsunamis don't just come and go. Often, the first wave is followed by second and third surges that can be just as deadly or worse. These delayed waves can trap first responders, overwhelm temporary shelters, and devastate people who thought the danger had passed. After the water recedes, the damage it leaves behind is extensive. Contaminated drinking water, landslides, ruptured fuel lines, collapsed bridges, and washed-out roads. Then come the economic aftershocks. Vancouver's port is one of Canada's largest. If that port were disabled for even a few weeks, the effects would ripple across the continent. Supply chains would choke, imports and exports would grind to a halt. Insurance claims would skyrocket. Analysts estimate that economic damage from a Cascadia tsunami could reach into the hundreds of billions. And that's before factoring in long-term reconstruction and housing displacement. There's another silent vulnerability, one many people forget. A massive network of undersea fiber optic cables connects North America to Asia through the Pacific. These cables run dangerously close to tectonic fault zones. If they snap during a seafloor rupture, we're not just looking at physical damage. We're looking at an internet blackout that could last hours or even days, disconnecting global communications and digital infrastructure. That alone could disrupt financial systems, global trading platforms, and emergency coordination across continents. And if you're wondering how we got here, how a fault this massive was allowed to sit quietly for centuries, the answer lies beneath the soil, in layers of history almost forgotten, echoes from the past. Long before satellites and seismic sensors, there were whispers in the trees and scars in the land. Indigenous oral histories, centuries-old tree rings, and eerie layers of coastal mud tell the same story. Cascadia has ruptured before and violently. And if you know where to look, the past is screaming a warning. The most haunting evidence of Cascadia's fury dates back to January 26, 1700. On that winter night, something massive struck the Pacific Northwest. Coastal forests suddenly sank, entire shorelines disappeared underwater, and soon after, a colossal wave surged across the Pacific. In Japan, over 7,000 kilometers away, fishermen documented a tsunami from nowhere that battered the coast with no warning of the quake. It wasn't until centuries later that geologists connected the dots. What the Japanese called an orphan tsunami was actually born in Cascadia. Along the Pacific Northwest, soil samples taken from marshlands and estuaries tell a tale of sudden destruction. In places like Copalis River in Washington and Neskowin Ghost Forest in Oregon, layers of sand sit eerily between peat and mud. This sand was not placed there gently. It was hurled inland by a massive tsunami, drowning trees where they stood. The trees died quickly with roots still intact, bark still clinging. But here's where science gets creepy. Tree ring dating on those ghost forests shows the trees all stopped growing in the winter of 1700. The same time the tsunami hit Japan. And those trees aren't alone in telling the tale. First Nations oral histories up and down the coast speak of a night of shaking, thunder, and waves that swallowed entire villages. The Huayat, Makah, and Haida peoples have preserved stories passed down for generations. Stories once dismissed as myth, but now backed by hard geological evidence. These are not bedtime tales. They're survival guides. Then there are the ghost towns of the sea, once thriving underwater ecosystems that vanished in an instant. Researchers studying the ocean floor off British Columbia have discovered disrupted sediment layers, tsunami-deposited sands, and fault scarps that run for hundreds of kilometers, signatures of a megaquake. These clues sit like crime scene evidence, waiting for someone to read them. But if 1700 was the last big one, how often do they occur? Paleoseismic data from deep cores in coastal marshes suggest that full-margin ruptures, megaquakes spanning the entire Cascadia Zone, happen every 250 to 500 years, sometimes sooner, sometimes longer. And that's what has scientists worried. It's now been over 320 years since the last one. The clock isn't just ticking, it's past due. More recent studies using offshore drilling and radiocarbon dating have found evidence of at least 19 full-margin quakes in the last 10,000 years. That averages out to about one every 520 years. But smaller, segment-specific quakes, especially in the northern Cascadia near Vancouver, have occurred more frequently. Some researchers believe that the northern segment may rupture more often than the southern zone, which could spell bad news for British Columbia. Yet, despite the mounting evidence, modern infrastructure still treats Cascadia as a low-risk zone. Many of Vancouver's buildings, schools, and hospitals are not built to withstand a magnitude 9. And while Japan and Chile have integrated ancient quake lore into urban planning, Canada has been slower to act. But if the past has warned us, what does the present have to say? As we'll see in the next chapter, the Earth is already whispering through tremors, and some of them are getting louder. Deep tremors and silent slips. Beneath the forests and coastal towns of southern Vancouver Island, the Earth is murmuring, but not in a way that breaks dishes or topples buildings. This is deeper, quieter, and to geologists, possibly even more ominous. The phenomenon is called ETS, episodic tremor and slip, and it might be the most subtle way nature warns us that something much bigger is brewing beneath our feet. ETS events are like a whisper between tectonic plates. They occur where the Juan de Fuca plate is slowly diving beneath the North American plate, deep within the fault zone, far below where humans can feel them. These slips don't cause traditional earthquakes. Instead, they involve the plates sliding past one another slowly over days or weeks, producing low-frequency tremors that only sensitive seismic equipment can detect. Normally, these events happen on a fairly regular schedule, like the fault zone breathing in and out, but recently, that rhythm has changed. Over the past 2 months, more than 2,300 tremors have been detected beneath southern Vancouver Island. That's nearly 3 times the typical number during a standard ETS cycle. Even more unsettling is the direction of movement. The tremors aren't staying put. They're migrating northwest directly toward what geologists call the locked segment of the fault. This locked segment is where strain is building, held in place by friction between the tectonic plates. It's been quiet for centuries. When the plates finally break loose, it's likely to happen there, releasing all that pent-up energy in a massive, high-magnitude quake. And now, ETS tremors are creeping toward that locked zone at a rate of about 10 kilometers per day. In geological terms, that's a sprint. Why does this matter? Because these tremors, though small, can shift stress around the fault zone. Think of it like tapping on a fragile window. Each tap might not break it, but the accumulated pressure eventually will. ETS is essentially the tectonic version of tapping, and now it's tapping at the most vulnerable spot on the Cascadia Subduction Zone. But the tremors aren't acting alone. Satellite data and GPS readings from ES's Sentinel-1 mission and Canadian ground stations are detecting simultaneous vertical uplift and horizontal shifts in the region. The coastline isn't just slipping, it's lifting. These shifts suggest elastic rebound. The land is stretching and straining like a rubber band, and when it breaks, the result is a seismic event. Geologists are especially focused on fluid pressure changes recorded during these ETS cycles. When the plates slip, fluids trapped deep underground can migrate upward through tiny cracks in the crust. This fluid movement weakens the surrounding rock, lubricating it and making it more prone to rupture. The combination of ETS, crustal deformation, and rising fluids is a dangerous cocktail, one that has preceded major earthquakes in other parts of the world, including the magnitude 8.1 quake in Japan's Nankai Trough in the late 1990s. What's alarming is that the current tremor activity around Vancouver Island is closely mirroring that same pattern. The speed, the scale, the direction, all of it aligns with what was seen in regions that later experienced devastating earthquakes. Scientists caution against making direct predictions. Earthquakes remain chaotic and hard to forecast. But the growing consensus is that this isn't just background noise. It's a clear sign that the system is shifting, and not in a good way. What makes ETS particularly deceptive is that the public can't feel it. Unlike traditional foreshocks or warning quakes, ETS doesn't rattle windows or wake people up in the night. It slips beneath our awareness, literally and figuratively. Yet it could be the closest thing we have to an early warning system, if only we learn to interpret it correctly. So what happens next? If ETS activity continues to accelerate and migrate, pressure may be pushed directly into the heart of the locked zone. And if that zone gives way, the result could be a rupture spanning hundreds of kilometers, releasing a quake in the range of magnitude 8.5 to 9.0, followed by tsunamis and aftershocks that would reshape the Pacific Northwest. But if these deep tremors are just the warning taps, then the next chapter asks the real question: what happens when the glass finally shatters? What's at risk when the fault snaps? When we talk about the Cascadia Subduction Zone, we're not just talking about shifting rocks beneath the ocean floor, we're talking about the fate of millions of lives and the delicate infrastructure that supports them. Stretching from Northern California through Oregon and Washington and into British Columbia, this seismic monster sits ominously offshore, quietly storing energy over centuries. And if the locked fault were to suddenly rupture in a full margin event, which geologists now warn is not a question of if, but when the Pacific Northwest could face one of the deadliest natural disasters in modern history. Let's start with the immediate impact: ground shaking. Cities like Vancouver, Victoria, Seattle, and Portland are all within reach of the most intense seismic waves. In a magnitude 9 quake, shaking could last anywhere from 3 to 6 minutes. Not seconds, but minutes. That kind of sustained movement isn't just enough to rattle windows, it can reduce entire neighborhoods to rubble. Many buildings in these cities, especially older ones, were not built to withstand major quakes. Despite recent seismic code upgrades, thousands of structures remain vulnerable, including critical hospitals, schools, and emergency centers. And the real danger, the shaking, doesn't come alone. Within minutes, a massive tsunami would begin to form off the coast. In some areas like Tofino or Ucluelet on Vancouver Island, it could reach shore in under 20 minutes. For coastal communities without robust evacuation plans or those caught with damaged roads and bridges, the chance of escape drops dramatically. And this isn't just a single wave. Historically, tsunamis from subduction zones come in sets. The second or third waves can be even more destructive than the first. Low-lying towns like Port Alberni and coastal parts of Seattle and Vancouver would likely face catastrophic flooding. Emergency warning systems, while improving, are not guaranteed to function in the chaos following a megaquake. The loss of power, telecommunications, and transportation infrastructure could paralyze the region's response capabilities just when they're needed most. But it's not just lives and buildings at risk. Think about the economic fallout. The ports of Vancouver, Seattle, and Portland are vital arteries for North American trade. If these were disabled, it would freeze the movement of goods, including food, fuel, and medical supplies, across the continent. Coastal refineries and pipelines could rupture, and underwater fiber optic cables, essential for internet and communication, could be severed, creating a digital blackout for millions. And then there's the issue of displacement. Tens of thousands of residents, possibly more, could be rendered homeless overnight. Shelters would be overwhelmed, water sources could become contaminated, hospitals may be unreachable or incapacitated, entire communities could be forced to relocate, not just for days, but for months or even years. The recovery timeline for a full Cascadia rupture has been modelled in some reports at 10 years or longer, and that's assuming consistent funding and political will. Inland cities may escape the water, but not the aftershocks or secondary effects. Landslides, fires sparked by gas leaks, and hazardous material spills are all likely in such a widespread event. And in mountainous regions of British Columbia and Washington, dam failures become a terrifying possibility. Many of these dams were built decades ago without anticipating the scale of seismic activity now expected. Public preparedness remains inconsistent. While some cities have begun retrofitting programs, others are lagging. Education on tsunami evacuation routes is limited, especially in rural or economically disadvantaged areas. In recent drills, a concerning percentage of residents failed to reach safe zones in the allotted time. Emergency planners are aware of the risks and they're not sitting idle. The province of British Columbia has invested in updated tsunami modelling, emergency siren networks, and early warning pilot programs. But the truth remains, in the face of a full margin rupture, even the best-laid plans may be tested beyond their limits. If that's what the quake could do to us, wait until you hear what it could do to the ocean and the fragile ecosystems that call it home. The silent alarm beneath our feet. While much of the focus remains on satellite data and surface deformation, geologists have increasingly turned their attention to something far more elusive and arguably far more alarming: deep episodic tremor and slip events, known in the field simply as ETS. These strange seismic occurrences don't produce violent shaking. In fact, you wouldn't feel them at all without ultra-sensitive instruments, but they may be the subduction zone's way of whispering before it screams. ETS events happen deep within the Earth, where tectonic plates interact under immense pressure. In the case of Vancouver's subduction zone, these tremors originate roughly 25 to 45 kilometers below the surface. Here, the oceanic Juan de Fuca plate slides beneath the North American plate not in sudden jolts, but in long, drawn-out movements. These deep shifts can last for days, even weeks, producing low-frequency tremors that barely register on a typical seismograph but leave unmistakable signatures in geophysical data. Over the past few weeks, a sudden uptick in ETS activity has been detected beneath southern Vancouver Island. More than 2,300 tremors were logged 3 times the average rate for this region. More importantly, this swarm of tremors is not stationary. It's migrating northwest, moving at a pace of roughly 10 kilometers per day. That's fast in geological terms, and its direction is raising red flags. It's headed directly toward what scientists call the locked zone, the portion of the fault currently storing the most tectonic strain. The locked zone is a critical area. It's the part of the fault that hasn't moved in centuries, the same section believed to have ruptured in the magnitude 9 earthquake of the year 1700. It's also where the most devastating energy release is likely to occur when the fault finally breaks. The concern is that migrating ETS activity could be transferring stress into this fragile boundary, destabilizing it just enough to trigger a full-scale rupture. To make matters worse, new instrumentation installed across British Columbia is now detecting subtle changes in fluid pressure that coincide with ETS events. Scientists believe that as plates grind past each other at depth, they release trapped fluids from surrounding rock. These fluids may then migrate upward, weakening the overlying crust and reducing friction along shallow fault planes. In other words, they act as a kind of geological lubricant, making it easier for a massive earthquake to begin. And here's the kicker. Previous studies in other subduction zones, including Japan and New Zealand, have shown that ETS swarms sometimes precede major earthquakes. Not always, but often enough to take seriously. In Japan, the 2011 Tohoku earthquake was preceded by deep tremor migration weeks before the rupture. In New Zealand, similar patterns were observed prior to the 2016 Kaikoura quake. So, what are geologists doing about this? Right now, teams from Natural Resources Canada and the University of Victoria are watching this ETS sequence closely. They've deployed portable seismometers, fluid pressure monitors, and GPS trackers to get real-time data. And while no one is raising the evacuation alarm just yet, scientists are calling this a high-interest sequence, code for "we're watching very, very closely." But how do you warn the public about something that might not happen? How do you balance the need for caution with the danger of crying wolf? That's the delicate dance scientists and emergency planners are doing right now. They know the risks, they know the odds, but they also know how unpredictable tectonic systems can be. So, if the tremors keep pushing stress toward the surface, what happens next? In the next chapter, we explore the grim reality. What would a full-scale Cascadia rupture actually look like, and who would be hit first? When the ocean floor breaks. When we talk about earthquakes, we often focus on buildings, roads, and people. But what happens beneath the waves can be just as catastrophic. If the Cascadia Subduction Zone ruptures, it won't just shake the ground, it could rip apart the ocean floor. And that would spell disaster for one of the most diverse marine ecosystems on Earth. The subduction zone lies directly offshore from Vancouver Island, covering a seafloor region rich with hydrothermal vents, coral forests, and crucial fish spawning grounds. A major earthquake could instantly displace sections of the ocean bottom by several meters, rising or falling like tectonic elevators. These vertical shifts could obliterate fragile ecosystems that have taken thousands of years to form. Cold water coral reefs, deep-sea sponge fields, and hydrothermal vent communities would be buried under landslides or fractured apart in seconds. But it gets worse. Many parts of the subduction zone are capped with methane hydrates, ice-like compounds that trap potent greenhouse gases under pressure. A sudden upheaval could release these gases into the water column, affecting oxygen levels and potentially contributing to short-term climate effects. Not only would this choke marine life, but it could accelerate regional warming in ways we barely understand. Coastal estuaries, especially along British Columbia, would also face transformation. These critical nurseries for salmon and shellfish could be flooded with salt water, altering their chemistry for years. Some estuaries could be permanently reshaped, while others might disappear entirely beneath landslides or sediment plumes. That would disrupt commercial fisheries, threaten indigenous food sources, and trigger mass die-offs in already stressed wildlife populations. And it's not just marine species at risk. Migratory birds depend on coastal wetlands for nesting and refueling. A tsunami-driven alteration of the shoreline could destroy these stopovers, pushing birds off course and breaking critical migratory chains. Whole populations could collapse not just from direct destruction, but from habitat loss and starvation in the months following a rupture. But the question now isn't just what might happen, it's what we can do about it. So, how are scientists racing against time to decode the warning signs? The science sprint. In the heart of British Columbia's seismic uncertainty, a massive effort is underway to track every tremor, tilt, and tectonic twitch. Scientists are now in what many are calling a tectonic sprint, a race against time to understand and possibly predict the next big rupture along the Cascadia Subduction Zone. And this sprint? It's happening in real time, with technology straight out of science fiction. Across Vancouver Island and along the seafloor trench, a new generation of monitoring equipment is being deployed. On land, geologists have installed dozens of new seismic stations, borehole strain meters, and GPS sensors capable of detecting millimeter-scale crustal shifts. These instruments don't just capture earthquakes, they detect crustal bending, fluid pressure changes, and early warning signals buried deep within the earth. Some of the most advanced strain meters have shown unusual pressure patterns, ones that eerily mirror those recorded before the 2011 Tohoku quake in Japan and the 2010 Chile megaquake. That alone is cause for concern. Underwater, fleets of autonomous drones are scanning the seabed for heat anomalies, fault ruptures, and gas vents that might indicate stress building along the fault. These drones are equipped with magnetometers, temperature sensors, and high-resolution sonar that allow them to map the ocean floor like never before. They're looking for the precursors of catastrophe, cracks in the crust, shifts in pressure, or rising plumes of methane that signal tectonic movement. Satellite data has also become a frontline tool in this battle. The European Space Agency's Sentinel-1 radar system has captured ground uplift of up to 3 centimeters over a span of just 2 months, far above normal background rates. Combined with GPS readings showing lateral drift inland, it paints a picture of strain accumulating across a 200-kilometer stretch of fault. This kind of deformation is not something you want to see in a region that hasn't experienced a full rupture in over 3 centuries. The modeling community is equally active. Geologists and geophysicists are now using AI-assisted forecasting systems to simulate rupture scenarios based on current data. These models incorporate 4-dimensional geodynamics, adding the element of time to traditional 3-dimensional tectonic models. They simulate not just where a rupture could start, but how it might spread, how long it might last, and where the shaking and tsunami waves could do the most damage. This allows emergency agencies to prepare better, but it also reveals an uncomfortable truth. We're still guessing, just with better guesses. This story isn't over, not by a long shot. If you want to stay ahead of the next major shift, be sure to watch our follow-up on tectonic threats around the Pacific Rim, and drop a comment below on what you'd do if the big one hit tomorrow. Stay alert and stay curious.